Have you ever wondered how a machine knows your glucose is 6.4 millimoles per liter, or that your bilirubin is 18 micromoles per liter, all from a few drops of blood? What if I told you that every one of those numbers starts with a beam of light and a principle discovered almost 300 years ago? In this video, we will explore how colorimetry and the Beer-Lambert law form the foundation of nearly every chemical test performed in modern pathology laboratories. By the end, you will understand how a beam of light passing through a colored solution becomes a number that guides a doctor's decision. But before we can understand how light becomes data, how color turns into concentration, we need to go back to where it all began. Nearly 3 centuries ago, long before laboratories had analyzers or photometers, a few curious scientists were trying to answer a deceptively simple question. What happens to light when it passes through matter? Their experiments with tinted glass, colored liquids, and sunlight didn't just reveal the nature of light. They uncovered the fundamental relationship between light, color, and concentration. This was the birth of colorimetry, and it all began with work of Pierre Bouguer, Johann Heinrich Lambert, and August Beer, 3 minds whose discoveries still define how clinical laboratories measure chemical concentrations today. When scientists first began to study light in the 18th century, they were probably not thinking about laboratory diagnostics or blood tests. They were simply curious about how light behaved. In 1729, a French mathematician and physicist named Pierre Bouguer noticed that light became progressively dimmer as it passed through tinted glass or water. He may not have realized it, but that simple observation was the first clue to understanding how light interacts with matter. Bouguer's insight that light intensity decreases predictably with the thickness of the medium became known as Bouguer's law, the earliest foundation of photometry. A few decades later, in 1760, Johann Heinrich Lambert, a Swiss-German physicist and mathematician, built upon Bouguer's observations. In his book Photometria, Lambert described mathematically that the reduction in light intensity is directly proportional to the path length of the medium through which it travels. In other words, the farther light travels through a colored solution, the more it's absorbed. This relationship, known as Lambert's law, transformed light measurement from an observation into a quantifiable physical principle. Nearly a century later, in 1852, a German scientist named August Beer introduced the final piece of the puzzle. Beer observed that for a fixed path length, the amount of light absorbed by a solution also depended on the concentration of the absorbing substance. This became Beer's law. When scientists combined Beer's and Lambert's discoveries, they produced one of the most elegant and enduring equations in analytical science, the Beer-Lambert law, expressed as A equals epsilon multiplied by B multiplied by C, where A, absorbance, is the amount of light absorbed by the solution. Epsilon, which is molar absorptivity, is how strongly a given molecule absorbs light at a particular wavelength. This is constant for each compound. B refers to the path length, the distance light travels through the solution. C refers to the concentration, which is the amount of absorbing species. This simple formula, relating absorbance to molar absorptivity, path length, and concentration, became the mathematical backbone of quantitative analysis. From there, innovation took over, bringing the physics of light into the laboratory. By the late 19th century, inventors like Louis Dubosc and Joseph Lovibond built visual colorimeters that allowed chemists to match colors by eye. The 20th century brought the electronic revolution, photoelectric colorimeters, spectrophotometers, and eventually automated chemistry analyzers, all built on the same physical law. What began as an experiment with light and glass evolved into a universal principle that still governs how laboratories measure chemical concentrations today. Every modern chemistry analyzer, whether testing glucose, bilirubin, creatinine, or total protein, it still depends on that same law. The Beer-Lambert law didn't just revolutionize physics and chemistry. It created the very foundation of laboratory medicine, turning color into concentration and observation into data. At its core, colorimetry is a method for determining the concentration of a substance by measuring the intensity of its color. The logic is simple but profound. The deeper the color, the higher the concentration, as long as the path length and wavelength are kept constant. In the clinical laboratory, color is rarely intrinsic. Instead, analytes are converted into colored products through chromogenic chemical reactions. For example, glucose reacts in the glucose oxidase-peroxidase method to form a pink quinimine dye. Creatinine in the classic Jaffe reaction forms an orange-red complex with picric acid. Total protein in the Biuret reaction produces a violet copper protein complex. Iron in the Ferrazin method forms a magenta complex, which is measured at 562 nanometer. Each of these reactions generates a color whose intensity is directly related to analyte concentration. The wavelength at which the color absorbs most strongly is known as the lambda max, which is chosen to maximize sensitivity and accuracy. Using light near lambda max ensures that even small changes in concentration produce measurable changes in absorbance. Colorimetry operates exclusively within the visible region of the electromagnetic spectrum, usually between 400 and 700 nanometer. This is the portion of light that the human eye can perceive. Within this range, analytes or their reaction products absorb light of specific wavelengths, producing measurable color intensity. To measure this, colorimeters use colored glass or interference filters that isolate broad wavelength bands such as blue filters for yellow or orange compounds, green filters for red or violet compounds, and red filters for blue or green compounds. These filters allow colorimetry to measure only substances that are colored in the visible range, such as bilirubin, glucose chromogens, or protein copper complexes. However, this same strength is also its greatest limitation. Colorimetry cannot detect colorless substances or compounds that absorb in ultraviolet or infrared regions, where many biological molecules actually absorb. While colorimetry provided a revolutionary foundation for quantitative analysis, its practical constraints became clear as clinical chemistry advanced. These included limited spectral range, usually between 400 and 700 nanometers, which excludes ultraviolet absorbing molecules like nucleic acids or many enzymes. Fixed filters, which meant that only a few discrete wavelengths could be selected, reducing analytical flexibility and accuracy. Broad bandwidth, which allowed wide wavelength ranges, reducing resolution and sensitivity. Manual operation. Early instruments relied on visual comparison or single readings, limiting precision and reproducibility. To overcome these limitations, spectrophotometry was developed in the early 20th century. Spectrophotometers replaced simple glass filters with monochromators using prisms or diffraction gratings that could isolate narrow, specific wavelengths across a much broader range, from ultraviolet through to visible and into the near-infrared region. They also replaced visual detection with photoelectric sensors, providing objective and highly precise electronic readings. In essence, spectrophotometry is not a different principle, it's the technological evolution of colorimetry. To understand how colorimetry works, we need to start with light, specifically how light interacts with matter. When light passes through a colored solution, three things can happen. Some light is absorbed by the molecule, some is transmitted through the solution, and a small amount may be reflected or scattered by particles or bubbles. This simple interaction between light and matter is the foundation of quantitative analysis in clinical chemistry. Let's define the key terms. Incident light. This is the light intensity entering the cuvette. Transmitted light. This is the light intensity exiting the cuvette after some light is absorbed. The ratio of these two values, the light that gets through compared to the light that went in, is called transmittance. It tells us what fraction of the original light intensity successfully passes through the solution. The problem with transmittance is that it does not vary linearly with concentration. If you double the concentration of a colored solution, you do not have the transmittance because light absorption follows an exponential decay pattern. To make the relationship linear and mathematically manageable, we use a logarithmic scale absorbance. This logarithmic relationship is what makes the Beer-Lambert law so powerful. It transforms an exponential decay of light into a linear relationship between absorbance and concentration. For perspective, 100% transmittance means zero absorbance. A 50% transmittance means 0.301 absorbance, which means that half the light is absorbed. A 10% transmittance means 1.00 absorbance, which means that 90% of light is absorbed, indicating a strong colored solution. A 1% transmittance translates into an absorbance of 2.000, which indicates that the solution is very dark. So absorbance increases linearly with concentration, while transmittance decreases exponentially. This is why we use absorbance, not percent transmittance, for calibration and quantitative analysis. It gives a straight line relationship that obeys the Beer-Lambert law. Let's look at the inside of a colorimeter or a spectrophotometer. As you can see, it begins with a light source. This could be a lamp or LED which emits light of a specific wavelength. That light passes through a filter or monochromator for spectrophotometry, isolating a narrow band around the analyte's lambda max, which, as we mentioned, is the peak absorption wavelength. The filtered light enters the sample cuvette. After passing through, the detector measures the transmitted intensity. The instrument's microprocessor automatically calculates and displays the absorbance value. In most analyzers, the blank establishes incident light, which equals to 100% transmittance, which means an absorbance of 0. All sample readings are then measured relative to that baseline. Also, most analytical work is done in the range absorbance equals 0.01 to 1.5, where readings are both accurate and linear. There are a couple of reasons for this. Number 1, at absorbance less than 0.1, the solution is nearly colorless and the transmitted light is almost equal to incident light. Small fluctuations in lamp intensity, detector noise, or electronic drift can cause large percentage errors. At absorbance greater than 1.5, the solution is so dark that almost no light reaches the detector. The instrument becomes insensitive to small changes in transmitted light because the detector is near its noise threshold. Stray light entering the detector causes non-linearity. The Beer-Lambert relationship starts to break down. That's why analytical methods specify linear working ranges. If the absorbance is higher, the sample is automatically diluted and remeasured. Before a single absorbance reading is taken, the accuracy of a colorimetric result, or for that matter any result, depends on the quality of the specimen. Errors introduced during patient preparation, specimen collection, sample transport, processing, and storage can affect absorbance reading long before analysis begins. The most common interferences arise from haemolysis, lipaemia, and icterus, each affecting how light interacts with the sample. Haemolysis adds extra absorbance from free hemoglobin. Lipaemia scatters light, increasing apparent absorbance, and bilirubin absorbs strongly in the blue region, reducing the true signal. Good pre-analytical practice, correct tube selection, proper fasting, prompt centrifugation, and protection of light-sensitive samples such as bilirubin is essential to minimize these effects. Even the most advanced analyzers cannot correct a compromised specimen. That's why maintaining specimen integrity is the first and most critical step in achieving reliable colorimetric results or any laboratory results. Once a high-quality sample reaches the analyzer, the next step is to transform that chemistry into measurable data. This is where the Beer-Lambert law comes to life. As light passes through the solution, the instrument converts changes in absorbance into precise numerical values. Let's look at how this analytical process unfolds step by step. Every colorimetric assay in the laboratory follows the same logical sequence. A cuvette containing only reagent, which is known as reagent blank, is used to set the 0 point or the baseline. A series of standards, which are solutions with known concentrations, are used to create a calibration curve. Patient specimen reacts with reagent to form a colored product. The instrument measures absorbance at lambda max and converts absorbance into concentration using the calibration curve. These steps are automated in modern analyzers, but the principle using Beer-Lambert law is the same. For colorimetry to remain accurate, several variables in addition to pre-analytical factors must be controlled. These include instrumental factors. Leaks around filters or mirrors can falsely lower absorbance, especially at high concentrations. Measuring off the lambda max reduces sensitivity and introduces bias. Fingerprints, scratches, or bubbles on the cuvette can scatter light and cause random error. Enzymatic reactions are temperature dependent. 37 degrees Celsius is standard for many assays. Chemical factors. Expired reagent or contaminated reagents yield weak colors, therefore compromising results. Insufficient incubation causes underestimation. pH and ionic strength affect color development and molar absorptivity. Biological factors. Hemoglobin absorbs light around 415 nanometer, which can result in false absorbance in blue region. This can be mitigated by checking haemolysis index and recollecting non-hemolyzed sample if needed. The sample cloudiness from lipaemia can scatter light, resulting in falsely high absorbance. Sample can be ultracentrifuged or a serum blank can be used to avoid interference. Bilirubin absorbs blue light, which can result in falsely low result in peroxidase assays. Dual wavelength correction can be used to compensate. Also, certain drugs and metabolites, such as cephalosporins, can also interfere, leading to higher result. An example is the creatinine Jaffe method. Use of enzymatic method in this case can mitigate the interference. Even when every factor from sample quality to wavelength accuracy is perfectly controlled, true analytical reliability still depends on one final element: quality assurance. Colorimetry is not just about optics and chemistry. It's about proving that every result is consistently right day after day. Before any test result can be trusted, the instrument must first be calibrated. Calibration ensures that the instrument's absorbance concentration relationship is correct, usually with traceable multi-point standards. In practice, several standards of known concentration are measured to create a multi-point calibration curve. This curve becomes the analyzer's reference. It allows the system to translate absorbance readings from unknown samples into accurate concentrations using the Beer-Lambert equation. Routine calibration ensures that the analyzer's optics and software are aligned and that any drift in lamp output or detector response is corrected. In other words, calibration anchors measurement to reality. Once calibrated, the instrument's performance must be continuously verified. This is achieved through internal quality control, the daily process of testing control sera with known target values at both normal and pathological levels. Each control result is plotted on a Levy-Jennings chart, providing a visual trend of analytical stability. To interpret these data, Laboratories use Westgard rules, which detect whether deviations arise from random error, for example, a pipetting variation, or systematic error, such as a calibration shift. If a control falls outside acceptable limits, patient testing is paused until issue is identified and corrected. This system ensures that every patient result released by the laboratory is not only accurate, but verifiably accurate. But precision within a single laboratory is not enough. Through external quality assessment, identical samples are distributed to many laboratories, for example, through the RCPA Quality Assurance Program in Australia. Each laboratory reports its results, and the data are compared to detect bias or systematic differences. That way, a glucose result of 6.8 millimoles per liter means the same thing in every accredited laboratory. Laboratory performance is not based on trust. It's demonstrated through accreditation. Standards such as ISO 15189 and NPAC guidelines in Australia requires laboratories to document every aspect of their analytical process, including calibration with certified reference materials, continuous internal and external quality monitoring, maintenance and service logs, and evidence that every assay is traceable to a reference method. This framework ensures that laboratory measurements are consistent, traceable, and internationally comparable. It also enforces the idea that accuracy is not a single event, it's a continuous state of compliance. So when an analyzer reports a glucose of 7.2 millimoles per liter instead of 6.9 millimoles per liter, that difference might appear trivial, but behind it lies a vast system of calibration, quality control, external benchmarking, and accreditation. That 0.3 millimoles per liter difference is not just a number. It represents analytical precision, quality assurance, and the collective discipline of clinical laboratory science. As mentioned, colorimetry is far from theoretical. It's the core of clinical chemistry. A few examples include glucose, creatinine, bilirubin, total protein, iron, and urea. In each case, the analyzer transforms optical absorbance into clinically meaningful numbers. Even small analytical errors can have serious consequences. For example, a few micromoles difference in neonatal bilirubin can change a treatment decision. That's why understanding colorimetry is not optional for laboratory professionals. It's essential to ensure that laboratory results are reliable, traceable, and safe for patients. Although powerful, Beer-Lambert's linearity holds true only under specific conditions. Deviations occur when concentrations are too high, causing self-absorption or scattering. Light is polychromatic, not monochromatic. Chemical reactions change epsilon or molar absorptivity, such as shifts in pH or temperature. Turbid samples introduce scatter unrelated to absorption. When these conditions arise, laboratories compensate by diluting samples, using bichromatic readings, or employing alternative methods like turbidimetry, nephelometry, or mass spectrometry. Understanding the limitations allows scientists to recognize when Beer's law works beautifully and when it needs a helping hand. So the next time you see a glucose or bilirubin result on a report, remember, it all begins with light. A single beam passing through a colored solution, obeying a law discovered centuries ago, still powers modern laboratory medicine today. But have you ever wondered what happens inside the analyzer? How that light is produced, filtered, and measured with such precision? In the next video, we will open the lid and explore spectrophotometry in clinical pathology, the technology that brings the Beer-Lambert law to life. With that said, see you in the next video.